Is this the worst one? Does this deserve the name?
Well, I think it's a new class. It's the first CPU bug that we're aware of that isn't a side channel. I don't think there's even a word for it. It's like a front channel. You can basically just read state out of the register file that doesn't belong to you. And as far as I know, we've never seen a bug like that before. So that's pretty exciting. So I don't know whether it's the biggest, but it's the most exciting.
This was Tevis Ormandy talking about a CPU vulnerability he discovered in Zen2 CPUs from AMD. And this is what he's talking about. These few assembly instructions exploit the issue. Tevis also gave this a name. He called it Zenbleed, which is a homage to the famous Heartbleed vulnerability, but also to Cloudbleed, which is the name of an issue Tevis found a while ago. Also, I just realized there is a CPU issue called Redbleed as well. Anyway, lots of bleed vulnerability exist, and Zenbleed, like the other bleed vulnerability, this one also leaks data. In particular, it can leak data from other processes running on the same CPU. You can see it here in action on my Minecraft server. It leaks a lot of Minecraft server memory.
The amount of data that you can leak, especially on if you're using hyperthreading, is just huge. It's just as fast as you can read them.
So yeah, this is a very serious issue, especially for the cloud, because there customers often share the same CPU. You could run Zenbleed and it can leak session tokens or passwords from a web server running by another user. So yeah, it's bad. And that's why I really think Zenbleed is a huge deal and it deserves to get more attention. So let's have a closer look and understand how it works. In the last video, I talked to Tevis about the discovery process, how he used fuzzing to find the issue. As a hacker, this discovery process is actually the most interesting aspect, because this is where I can learn about new approaches and new ideas, which I might be able then to use when hacking something else. But of course, exploiting vulnerabilities is also fun. So let's come back to this minimal snippet and try to understand it. There are only 5 instructions, so how hard can it be? But admittedly, those I have also never dealt with. And on top of that, for me, just looking at the snippet by itself, this still feels a bit too isolated. I want to understand how the whole exploit works, not just the trigger. So let's pull up the complete source code and let's have a look. Google has made the code available here on GitHub in the security research repository. Here you can find several files, but zenbleed.c and zenleak.asm are the important ones. Because the exploit snippet was assembly code, let's start with that one. Inside the zenleak.asm file, we can actually find a surprising amount of assembly code. There are actually multiple variants for the same issue. Zenleak Pepo Unrolled, Zen2 Leak Bench Pause, Zen2 Leak SLS in SRB, Zen2 Leak Train MMO 0, and Zen2 Hammer XMM Registers. I think it's very interesting that there are different variants, because this allows us to compare and look for patterns. What do they all have in common? This should help us to identify the important parts. So let's start. What do they all have in common? Well, all of them contain the instruction vzeroupper, so clearly that's important. But there's more. Before the vzeroupper, we always have some branches, mostly conditional jumps. Here, for example, JPE, jump to over 0 when parity flag is set, or here, jump if sign flag is set. But that's not all. There are more patterns. Before the branches, we always have a move instruction, vmove DQA or vmove UPD. The instruction names look a little bit crazy, but it's just a move, like move EAX. So yeah, while there are different variants, at the core they are quite similar. So let's just pick one to focus on. For example, Zen2 Leak Pepo Unrolled. But before we look closer at the assembly code, where is it even used? How does it fit into the bigger picture of the whole exploit? Looking into the Z code in zenbleed.c, we can see that our Zen2 Leak Pepo Unrolled is referenced as an external function and placed in this list of variants. When you execute the exploit, you can select a variant, and whichever you choose is then set to the zenleak callback. So this is now a function pointer pointing at our assembly snippet. And if we look for when the function is finally getting executed, we can find the thread leak producer function, which calls it here. Also, it's passing in a pointer to a variable named register buffer. And apparently, if we leak data, it will appear in this buffer. This leaked value is then handed over to other parts of the program, saving it to a cache and adding it into a queue to be later processed by the leak consumer thread. This function is executed by another thread, and it just takes the leaked value, checks maybe if it's a valid string, and then prints it out. And this is the familiar output you have seen in the terminal before. Cool. Now that we know what the C code of the exploit generally does, we understand the bigger picture. So let's start dig deeper and look at where the real magic happens. So far, we only know that we pass in a pointer and magically leaked data appears. So what is happening here? Let's go back to the zenleak.asm file and have a closer look at the code. This assembly code might look a little bit scary at first, but it's important to know that any line with a percentage sign is not assembly code. Those are instructions for the compiler used when the code is compiled. You can use these compiler preprocessor directives to help you in the assembly code generation. And so the first directive we can see is a macro. Here's the start and end of a macro called zenleak. Macros you can imagine like functions. I mean, they are functions, but not in the code. They are functions that get executed in a preprocessor step during compilation. And they return assembly code, which is then in the resulting binary. Anyway, the real assembly code starts here with the XOR RAX, basically setting the RAX register to 0. Then there are more percentage lines, so the next real instruction is the jump to repeat. So here we have an endless loop. So what exactly are these preprocessor directives doing now? Well, these are helper functions to generate assembly code dynamically during the compilation. And it's almost self-explanatory. First, a variable reg is assigned the value 15. Then we create a repeat block that we execute 16 times. And inside this loop, we call the zenleak macro with the reg value and decrement the reg value. So you can imagine this like a for loop, where it counts down a reg from 15, 14, 13, and always calls the macro zenleak reg. And remember, this is done during compilation time to generate assembly code. Let me actually show you the result. I'm using GDB to quickly print the assembly code of this function, and this function is actually pretty long, much longer than we can see here. But you might notice these repeating blocks. They are made up of the instructions from the zenleak macro, just with decrementing YMM registers. And this is what the preprocessor directive did, generating a long list of instructions trying to exploit Zenbleed on different YMM registers. But of course, these blocks are basically the same. So let's just pick one of them and we can then take a closer look. But sorry, before we take a closer look at these instructions, we need to take a small detour, because I think for many of you, you haven't really seen these XMM and YMM registers before, or you don't know what they are. So let's have a quick crash course. If you watched my older content, you probably have some basic assembly knowledge, and you probably know that the CPU has various registers that you can use to handle data during execution. For example, there is EAX or RAX, or EIP, the instruction pointer, SP, the stack pointer. There are lots of different registers. However, there are actually a lot more registers in modern x86 CPUs than these here. For example, YMM and XMM. Actually, there are lots of them. They go from XMM or YMM 0 to generally YMM 15. So there are 16 YMM registers in total. And now you also know why we generated the zenleak block 16 times. We generated it for each YMM registers. Anyway, you probably know that registers like RAX are 64-bit large, which makes sense on a 64-bit CPU. But these XMM and YMM registers, they are actually 128 and 256 bits large. They are massive. Also, they are similar to RAX and EAX in the sense that EAX and RAX are not separate. EAX references the lower 32-bit of the whole 64-bit RAX register. And so XMM0 is basically the lower 128-bit of the 256-bit YMM register. Pretty crazy, right? But what are they useful for? Well, look at the Wikipedia article for Advanced Vector Extensions AVX. AVX uses 16 YMM registers to perform a single instruction on multiple pieces of data. Each YMM register can hold and do simultaneous operations, math operations, on 8 32-bit single precision floating point numbers or 4 64-bit double precision floating point numbers. This is pretty fancy. You can take 8 numbers and do math operations simultaneously on them. So these registers and the AVX instructions are pretty useful for doing any kind of calculations. But it's not only useful for math, because it turns out it's also useful when doing string comparisons. If you do a bit of exploitation CTF challenges, you might have run into this before. Here's a small C program just doing a string comparison with a 24 character long string. Let's compile it and test it. If we enter a wrong input, we get fail. If we enter the correct string, we get correct. How does this look in assembly? Let's launch GDB and set a breakpoint in main, run it, we hit the breakpoint, and now we can single step forward. We reach the string compare, and the string compare is obviously not implemented by us. We go into the assembly code of the libc library and look at how the string compare is called here. String compare AVX2. AVX2, also known as Haswell New Instructions, expands most integer commands to 256 bits and introduces new instructions. So libc implemented here a version of string compare using the AVX2 features of our CPU. And you can already see that it starts to use XMM and YMM registers. Here, for example, is a vector move YMM1 from the address pointed to at RDI, and RDI is our first parameter when calling string compare. So this string is now moved into YMM1. If we print the YMM register, we see that it at first is all 0, but if we execute the move and look again, we see that the whole string 0001111 is stored in a single YMM register. That's so much data in a single register. Crazy, right? So you can see these YMM registers and AVX instructions are not just useful for doing math stuff, but it's also used in lots of string handling. And that's also why this issue is so bad. Because, spoiler alert, it leaks a lot of string data because of this. Anyway, after this crash course and about AVX instructions and the YMM registers, let's finally start to look at the Zenleak code. What does it do? First, it calls VP XOR on YMM0. So this will just clear out the whole register, setting it to 0. Then the next instructions, VP compare whatever, doesn't seem to be important, just used for scheduling. I removed it and the exploit still worked. It's just a bit slower. So it just seems to be an optimization that Tevis figured out, which means let's just ignore it. Next we have vCVT-SI to SS, which stands for convert one single quad word integer from RAX to one single precision floating point value in XMM0. Sounds crazy, but no worries, it doesn't really matter what exactly it does, because Tevis wrote, it's not important what CVT-SI to SD is supposed to do, I'm just using it because it's one of the instructions the manual says uses the optimization. And let's have a quick peek into the manual from AMD. It says here the processor implements an XMM register merge optimization, which means the processor keeps track of XMM registers whose upper portions have been cleared to 0. If you look at the pseudocode of what this convert instruction does, it takes the source register RAX, which is only 64-bit, does a number conversion on it, and it writes the resulting 32 bits into the target XMM register, which means all the remaining 96 bits up to the 128-bit, it will always be set to 0. And so this information can be used to bypass the usual result merging for the upper parts of the register. Again, don't worry about what that exactly means. I don't really know what it means either. I mean, we could read some more documentation about what it is supposed to do, but obviously there was a bug in the implementation anyway. And that's the thing with CPUs. We cannot really know what and how exactly the CPU does the optimization.
The CPU to us is entirely a black box. We only have the published documentation, which is very high level. And so we basically have to experiment and try things and see if that works. And if it does, then we have to make a hypothesis, test it, and then figure out if that's really what happened.
So don't get too hung up on what this merge optimization actually means. The only thing you should take away from this is that for this convert instruction, the CPU implements some optimization by remembering something about the upper bits being set to 0 by this instruction. And whenever there is intricate logic, it's a breeding ground for bugs. Anyway, let's come back to this assembly code. So after we zero the whole YMM register and we call this convert instruction that starts some crazy CPU optimization on XMM, we then perform a move with itself. This looks like a do nothing move, and it kind of is, but it actually does a bit more under the hood. And this is where I learned something new about CPUs from Tevis. We are now going one layer deeper. Earlier, we already looked a little bit at the GDB debugging output, and we have seen various different registers. And I always imagine registers to be actual physical locations. You know, I thought in the silicon there is a memory cell, and that is RAX or RSP. And this mental model worked fine for me for a long time. I also, for example, worked on Ben Eater's 8-bit computer, and here the registers are actually these memory chips. I can physically see the registers. But this mental model is not quite reality anymore, at least for modern CPUs. So here comes another level of complexity which allows CPUs to increase performance.
Because I think a lot of my audience knows the basics of exploitation, and I think lots of people have a good imaginations of how this register kind of okay, that's a physical thing. Can you maybe share what is the next step of understanding how a CPU actually works, kind of the next layer down maybe?
So when you write into a register, there isn't a single physical location on your CPU where that register is stored. There's actually something called a register file and a register allocation table. And the register allocation table manages this shared resource called the register file, which is kind of like a software heap. The register allocation table chooses where each register points to within this register file.
So in the CPU, there's actually a larger memory holding register values. And Tevis, being a software guy, thinks of it like a heap. It's just an area of memory that can be used to store register values. But this heap has to be managed and organized, and that's where the register table comes in. This can be imagined like a pointer table. YMM0 is stored here, and YMM1 is stored there. But that's not all. There's another layer of abstraction, and that is called register renaming. Imagine the following assembly code. We move a value from the stack pointer into RAX, we increment it, adding 1, and we move the result back into the stack. And then we do it again, just with a different value. All of this code is using RAX and thus depends on each other. But logically, these two blocks are independent. If the second part had instead used RBX, then the CPU could run both of them in parallel or execute them out of order. Maybe this memory value is already in the cache, so we could execute this while we wait for the memory of the first block. So this is where the register renaming on modern CPUs come in and enables out-of-order execution. So when register renaming is happening internally, the CPU is not really using RAX anymore. The code can be imagined to look like this. Instead of the register names we know, they get renamed to something more abstract. And then the register allocation table contains mappings where the values for reg1 and reg2 are stored in the register allocation file. And now we finally come back to the Zenbleed code. A move instruction apparently triggers a register renaming step, which appears to be important for the bug. If you thought this was already complex and mind-bending, then wait for the next step, because now comes the real CPU magic. After the register renaming from the move, we have conditional jumps, which actually always jump. We should never reach the vzeroupper. And this is where we enter the shadow world. We are entering speculative execution territory. So the CPU wants to be really fast, and it wants to execute code whenever it has capacity, which means if it has to wait on something, it might decide to keep executing the next instructions already. But the problem is, if you have a conditional jump, an if case, you might not know yet if we take the jump or continue. But let's just take a guess. If we are right, then we executed the code already. If we are wrong, well, we throw away the result and execute the real path. And so this can happen here. The CPU might mispredict where the condition jumps go and speculative execute vzeroupper. So what does that instruction do? I already mentioned that XMM0 is basically the lower part of YMM0. But XMM is older. The instructions that are operating on just XMM are called SSE instructions. They were introduced to Intel CPUs in 1999. YMM registers are newer. They were introduced in 2011, and their instruction extension is called AVX. So while XMM and YMM are kinda shared, they are also very different. And so there is an execution penalty when mixing AVX and SSE instructions. There's a significant penalty for mixing SSE and AVX instructions when the upper 128 bits of the YMM register contain non-zero data. Transitioning in either direction will cause a microfault to spill or fill the upper 128 bits of all the 16 YMM registers. There will be approximately 100 cycle penalty to signal and handle this fault. To avoid this penalty, a vzeroupper or vzeroall instructions should be used to clear the upper 128 bits of all YMM registers when transitioning from AVX code to SSE or unknown code. So while vzeroupper sounds like a basic instruction, just zeroing the upper bits of the YMM register, it's actually an important instruction for optimization. And optimization means we have another fancy complex feature that is a breeding ground for bugs. So let's come back to the code here. We know that when the CPU mispredicted where we execute next, the vzeroupper could have been executed. But that shouldn't have any side effect, right? Because it executed in the shadow world, speculative execution world. And as soon as the CPU realizes we actually jump here, the result from the vzeroupper is thrown away. But are the results really thrown away? For example, it could be that the shadow world loaded something into the cache, and you can later measure the cache access timing, which means the speculative execution world bleeds a little bit into the real world. Generally, this is where a lot of these famous CPU bugs attack. Meltdown Inspector, for example, but also the riddle bug that I showed you in another video. They all have something in common, and that is that they are side channel bugs due to mishandling of data during the speculative execution. If you are curious how these cache leaks work, definitely check out my riddle video. But Zenbleed is different. And now we come to the explanation of what Zenbleed really does, or at least my own speculation about what is happening, because remember, we don't really know what is happening inside the CPU. But it sounds logical to me. So I think during the number conversion, the CPU marked the upper bits of the register to be set to 0. But that takes time to do, and that's why there is the register merge optimization. For certain instructions, we can bypass the usual result merging for the upper parts of the register. And there's this whole XMM and YMM mixing that can cause big performance penalties unless we use vzeroupper to zero the upper bits. And that's why I guess the CPU looked ahead and sees a vzeroupper, speculative executes it, and now it assumes, well, my upper bits will be set to 0 down here anyway, so we don't need to care about the upper bits during the number conversion. But for whatever reason, during the rollback after the mispredicted speculative execution, this assumption was not reverted. Maybe because of the register renaming. Maybe the CPU did a rollback just on the wrong renamed register. Either way, the upper bits remain untouched. They are not zeroed as expected. But shouldn't it be 0 anyway because of the XOR before? Well, Tevis also explains that zeroing a register doesn't mean that zeros are actually written into the register file. Apparently, it's faster for the CPU to set a 0 flag. And so if the 0 flag is not set, the whole register will just point into the register file. And remember, Tevis imagined this register file like a software heap. This means it's possible that there was other register data stored in that location before. And suddenly we basically have like a use after free situation. We have a pointer into memory to data from an object that was freed before. And now we can simply read the 128 upper bits from the register, and we leak whatever data was there in the register file. And now it also makes sense why string comparisons using AVX instructions makes this issue even more exploitable, because not only math numbers were stored in these XMM and YMM registers, no, any string that gets compared could be located here in the file, and we can leak it. Boom. It's crazy how complicated CPUs are and what kind of bugs exist. And yes, this is a really bad issue. But there's also good news. This is not the end of the world. I asked Tevis, how could AMD fix this issue?
Like, can it be fixed like with a microcode update, or is it like an inherent flaw now of this architecture? Or
AMD are going to release a microcode update, and that's going to resolve the issue. They also have what are called chicken bits. And chicken bits are just bits that you can enable and disable features in the processor, and you use that by use that by setting bits in MSRs. And so they found a combination of features that can avoid this bug. And so that's going to be a backup if you can't apply the microcode update. And so what's going to happen is the Linux kernel is going to always set these chicken bits if it knows that your microcode is out of date. But if your microcode is up to date, then you don't have to worry that everything's fixed.
This is good news. However, my Minecraft server is still vulnerable. This was actually a small experiment for me. My Minecraft server is a dedicated server from Hetzner, and I kept looking at my emails, wondering if they would inform me about this critical security issue on my server. I understand that I'm just renting a physical server and I'm responsible for it. I obviously cannot blame Hetzner for any security issues in the software and web apps I run on my server. But to be honest, I did kind of expect them to at least inform me about the CPU issue, because they provide the hardware and this is a hardware issue. So I think they are a little bit responsible for informing me about it. It would have been cool if they had sent every AMD Zen 2 customer a quick notification, or maybe even provided documentation on how to fix it, because I have no clue how I can update the microcode of my server. But I can also understand if they say that I'm fully responsible for the machine I use, and that's also fair. What do you think? Write it in the comments below. Anyway, if you thought this vulnerability was interesting, I hope you have already watched part 1, where we learn about how Tevis or Mandy used fuzzing to find this issue. And if you know about that, then you might also wonder if there are more bugs to come. In case you didn't know, when Google reports vulnerabilities to other vendors, there is usually a 90-day disclosure deadline, which means there's one last question I want to ask Tevis.
Are you already working on the next bug? Are there other bugs already in the 90-day deadline?
We're working on it.